for this vector x such that all the constraints are satisfied as well as the function is minimized. So there may be several values for this x which satisfy these conditions, and it also gives a minimized value of for the function. So the set of all those functions, set of all those values are called feasible set, and they make up the feasible region. The optimization problem is to select the best of those feasible region. Okay, so the optimized point x star is such that the function's value at that point is less than equal to the function's value at all other feasible points x in the domain of the function. So such a point is called optimal point, and the function f of x is called the objective function. That is the goal, that you have to minimize this function. So this is classified into linear and non-linear problems. Linear programming problems or linear optimization problems are the ones which are having linear objective function, and non-linear programming problems are the ones which are having non-linear objective functions. Okay, in machine learning and neural networks, usually you come across non-linear objective functions. Further, the techniques can be divided into classical and non-classical. So classical techniques basically make use of derivatives, differential calculus, and non-classical techniques, they are based on some numerical techniques. So we won't be dealing with the non-classical ones in this lecture. However, there are ways in which the neural network is expressed as a constrained optimization problem. In those cases, numerical techniques are used. In general, the neural networks are expressed as unconstrained optimization problem, nonlinear optimization problem, and classical optimizers are used to train the neural network. So there are several classical optimizers which have been developed over the years to cater to many challenges that arise due to either data set or features or gradient or several others which we will see in due course of time. So one other limitation of classical techniques, which is an open problem also, is that it cannot be applied to non-differentiable and discontinuous. First point of view, we are looking at the minimization of an objective function, and that too in an unconstrained manner. That is, we will not be having any constraints for the neural network. So before we move further, we need to understand what is meant by local minima and local maxima. First, we will look at it in a single variable context. That is when the function is only of one variable. For example, this function f of x is continuous and is defined on a closed interval AB belonging to R. So point x is equal to x star is said to be a local minimum if the function's value at that point is less than equal to the function's value in its neighborhood. That is, if you take any subset of this interval, supposing this is the subset of this interval, this subset. So in this subset, supposing this is the local minimum point, then the value of the function at this point is going to be less than the value of the function at all the other points which are here or which are here. So this is the local minimum which is constrained to a subset. Similarly, you can define the local maxima, which is a point in a subset for which the function's value is greater than equal to all other points in its neighborhood. Okay, so this is your local minima and maximum expressed mathematically as well as graphically. Similarly, we define the global minimum or the absolute minimum that we call it. So what it is, it is the same as local minimum but extended to the entire domain of the function. So supposing you have a single variable function, the global minimum is the point at which the function's value is the lowest as compared to all other points in the domain, as you can see here. So this graph also has a local minimum and a local maximum. So you can see that why this is local minimum, because the function's value at this point is less than equal to these points only. That is the points in its neighborhood only. So this is the local minimum and this is the global minimum for which the function's value is less than equal to the function's value at all other points in the domain. Similarly, you define the global maximum at which the function's value is greater than equal to the function's value at all other points in the domain. So this is the concept of global minimum and the local minimum. So optimization problem strives to determine a global minimum if it exists, if it is possible, or at least a local minimum, such that the function's value is minimized. Or in with respect to a neural network, the uh, the optimization problem is to minimize the error between the predicted value and the original value, okay, such that you have a local minimum at least. Okay. Okay. So there are more points which are also called as critical points, stationary points, and the inflection points. So stationary point is if the function has either a maximum or a minimum. So this is a bigger umbrella in which we say that any point which is maximum or minimum can be said to be as stationary point. Point of inflection where the function is neither maximum nor minimum. So that means the curvature changes, but you don't have the actual minimum or maximum here. So what happens is that at maximum point, the function is changing from increasing to decreasing. At a minimum point, the function is changing from decreasing to increasing. But at the point of inflection, there is a change, but there is only a curvature change. There is no extremum at this point. So these are the stationary points. How to determine these stationary points? So again, this graph shows you the various points that we have just learned: the inflection, point of inflection, the global minima, global maxima, and the local minima. Okay, so this is the global maximum because the value of the function at this point is greater than the function's value at all the other points in this domain. So this is the domain of the function. This is the point of inflection because at this point, if you take the function's value, the function's value at this point is less than the function's value at this point, and the function's value at this point is less than the previous. I mean, it is greater than the previous point. So that is why this is the point of inflection. Whereas in the global minimum, the function's value is always less than equal to the function's value at every other point. So this is about the various points, the visualization of all the stationary points that are existing. Now we come to determining the stationary points. So this concept already we had used in linear regression for minimizing the residual sum of squares and finding or estimating the coefficients for the residual sum of, I mean, for the linear regression. So the condition is called the necessary condition for the existence of stationary point. So a function is, if it is a single variable function and is continuous and differentiable, so the at stationary point, the function is the derivative, first derivative of the function is going to be 0. So this is the condition that we used yesterday also. So this condition will give us the stationary point. They will not let us know whether the stationary point is a minima or maxima or point of inflection, but it will only tell us whether the point is a stationary point or not. The next condition, that is the sufficient condition, gives us the nature of the stationary point. That means, so if the function has continuous derivatives of say every order in the neighborhood of this stationary point, then the following criterias will tell us the nature of the stationary points. So the stationary point will be a local minimum if the nth derivative at that point is greater than 0 and n is even. The stationary point will be a local maximum if the nth derivative of the function at that point is going to be less than 0 when n is even. So if n is odd, that is, if you have the odd derivative not equal to 0, the nth odd derivative not equal to 0, then you cannot say anything about the point. So that is that it is a minimum or maximum. You have to say that the point is inflection. It is the point of inflection. So this is the sufficient condition which tells us about the nature of the stationary point. Now, the limitations of this theorem are that it does not tell what happens if the minimum or maximum point is at the end point. Okay, I mean at the end points you cannot make any inferences. Okay, the theorem is not valid for the endpoints. It only checks in the interior of the domain. Second limitation is that the theorem does not say what happens if the function is not differentiable. For example, if you have the function f of x is equal to mod x. So we all of us know this function very well, that this function is not differentiable. F of x is equal to mod x is not differentiable at x is equal to 0. Okay, but uh, uh, the minimum point for mod x is 0 only. So this function is a very good example of this theorem failing at the minimum point. Using this theorem, we cannot identify the minimum point of function f of x is equal to mod x. Similarly, if you have a function f of x is equal to x square in a domain say -2 to 1, then also this test fails, the necessary and sufficient condition, because when you find the derivative it will be 2x and the stationary point will be x is equal to 0, but this function is having a maximum at x is equal to -2, which is the end point. So maybe we can write this down. So f of x is equal to x square, okay, in -2 and 1. So this function is having maximum at this endpoint -2, and the necessary or sufficient condition do not say anything about the nature of this function. Okay, so these are the two cases where this theorem, this result fails. So this is kind of an open problem. Now, in the context of neural network, so you have seen this neural network, the structure of this neural network in the previous lecture, and you also saw that this network has to be trained for optimum values of the weights. Okay, so for that you saw that the process has to be iterative. So we adopt two iterative optimizers or iterative optimization techniques which make use of derivatives and give us the output. So the first and foremost, the foundation of all the optimizers is the gradient descent. So gradient descent is an iterative optimization algorithm which is used to minimize a function by moving in the direction of negative of gradient, which is the direction of steepest descent. And the update rule for the function says that given a differentiable function, the value of the point at k plus 1th iteration is given by the difference between the value of the point at kth iteration and eta times the gradient of the function at the point xk. Okay, so we will see more of it. So in gradient descent, the update rule is basically, let us see how that update rule has come. So let us say that the t plus 1th point, the t plus 1th point is given as the previous point plus some difference. Now we are trying to solve a problem for minimizing the loss. Okay, for minimizing the loss. So that means we want this value to get decreased in every step. Okay, so that means this change has to point in the decreasing direction. Okay, so the L of x, supposing the L of x is a function that we want to minimize, that is the loss function in the neural network. And uh, in order to minimize this value, we want to iterate in such a manner that with every iteration, the value of the point should be decreasing. So that means this delta, this change should be a negative quantity. Okay, so let this be equal to some eta times dt. Okay, uh, our goal is to find such x which minimizes this L of x. Okay, so this means moving in a direction that lowers this value is what we want to do. So let us take this change to be some eta times dt, where dt is the descent direction. Okay, so what is the descent condition now? So the descent condition is gradient of this loss function transpose times this dt should be less than 0. Okay, where gradient of L of x t is pointing uphill. All of us know that the gradient points in the uh, steepest direction, that is in the uphill direction. So what we want is, we want this dot product of gradient of loss function with the direction to be pointing downhill. Okay, so for this dt to be negative, the most aggressive way is to decrease the function, is decreasing the function by moving in a directly opposite of this gradient. So if it is pointing, the gradient is pointing uphill, if you take the negative of it will point in the downhill direction. And that is why you take the dt to be negative of the gradient of L of x of t. Okay, so this is what we call the basic gradient descent. Okay, so the update rule here is xt plus 1 is equal to xt minus eta times gradient of L of x of t. So we have got this change to be negative as the negative gradient of the loss function at the point xt. Okay, so this is the steepest direction. Now in this graph you can see a plot. This is a contour plot of a function. Okay, a 2D function, and you can see here this red path. Okay, this represents the steps of the gradient descent. Okay, so notice how this path is curving towards the center. So this point is the minimum point, and this path is taking us to this point by following the steepest descent direction. And at every point this descent direction is changing and pointing towards the uh, um, steepest descent, taking us to the minimum point. Okay, so this is the basic base of gradient descent, which forms the foundation of all the other optimizers that we are going to look at in this lecture. In fact, these are the optimizers which are popular for training the neural network. Okay. And eta, here eta is the learning rate. It is a scalar which is greater than 0, and this is basically the hyperparameter which needs to be tuned well in order to train the model. So when you train a neural network, you always have certain kind of hyperparameters, and training a neural network is all about training the weights, optimizing the weights, and tuning the hyperparameters. So this is one of the hyperparameter in gradient descent. In gradient descent, you have only one hyperparameter, that is the learning rate. In the optimizers that we are going to look at will have more than one hyperparameters in terms of learning rate only, or the momentum or adaptive learning rate and so on. So these needs to be tuned with, and there are ways to tune it. You can adopt meta heuristic optimization, or you can empirically look at the results by giving different values learning rate, and then you see what is happening to the result that you have got. So the learning rate is totally empirically decided. Okay, so that is why I say that in order to train a neural network, the entire task is to optimize the weights, that is minimize the loss with optimized weights, and tune the hyperparameters. So advantages of this method is it's great for I mean for the function with convex, the functions which are convex. So we will see what convex functions are in my next lecture, that is tomorrow, because I mean convex functions, what they ensure us, the theoretically it ensures us that if the function is convex, then you are guaranteed to have one minimum, and if it is strictly convex, then you are guaranteed that there is a global minimum. And gradient descent also works on the steepest descent direction with the help of gradient, so it takes a more direct path towards the minimum. So we are also sure that the path that we take towards the minimum is the path that is pointing to the steepest descent. There can be no other path that is so direct in pointing towards the minimum. So that such is the theoretical robustness behind this gradient descent algorithm. Now, the challenges with this gradient descent is that you have no guarantee of finding the global minimum. That is because of the function, the topology of the function. It can get stuck at the local minimum, and it is not suitable for larger data sets because it takes more computational time. So we will see how these some of these challenges are taken care with the optimizers that we are that we will come now. So before we do that, I want to illustrate this example of neural network using gradient descent. So here we want to train this two layer and two neurons, one hidden layer neural network with the help of gradient descent. So here you can see there are two inputs, one hidden layer, okay, and there is an output. So we saw in the previous lecture, this is how the mathematics of a neural network is. What you do is you sum the product of the weight and the inputs. So and then you apply the non-linearity to it to get your y. Okay, uh, so that is, so basically you are taking the bias plus you are doing the dot product of the weight matrix with the input matrix. Okay, so that is giving you the the uh, the input on which you are going to apply the non-linearity. Okay, and this process is continued with every layer. So this if you have one more layer, that layer will take the input from the previous layer, and so on. So with this background, we will try to numerically solve this problem. Okay. So we are assuming the weights, that is W11 to be 0.1, W12 to be 0.2, and sorry, W21 is 0.3, and 12 is 0.2. Then you have 22, W22 is 0.4. B1, the bias for first one is 1, and the bias for the second one is 1. That bias we are assuming as 1, and the second set of weights that are connecting the hidden layer with the output, we are assuming to be 0.1 and 0.6. Okay. And the nonlinearity, the activation function that we are taking is the sigmoid function. The label or the output, that correct output that we have is t is equal to 1. So first thing is to apply the forward pass. Okay. So let me go back to this, and maybe I can try to do it with the help of yes. So I'll just erase this. Yes. So we had this neural network with two inputs and one hidden layer and an output, and these are the weights that we are assuming. So now we will use the back propagation. First of all, we will use the forward pass. So in the forward pass, you have Z1 is equal to the first weight. So W11 X1 plus W12 X2 plus B1. Okay, so you had this. This is W11. This is W12. This is W21. This is W22. And then you have V1 and V2. And this is your the hidden layer, H1 we will call it, and H2. And this is your X1, and this is your X2. This is my So you have all the values for W11, X1, W12, X2, and B1. Similarly, you will have Z2, Z2, that is W21, sorry, X1, not W21, it will be W12 X1 and W22 X2. And here you will have to 1. So we want the weights which are going to 1, that is W11 and W21. And here we are taking the weights which are coming to uh, uh, 2 H2. So that is W12 and W22. So plus the bias. Okay. Z2, which is 1 upon 1 plus e power minus 7 1.7. So this is giving us the values for the hidden layer H1 and H2. Now we will find out the output, that is V1 H1 plus V2 H2. Okay, so V1 and V2 are the second set of weights which are connecting your hidden layer with the output layer. So zero point 0.5 is V1 and zero point 0.6 is V2. So V1 and H1 value that we have got from the previous step, and V2 and H2 value that we've got from the previous step. So that gives us the output, Z output. Now we will apply the non-linearity on this to get the final output, that is 1 upon 1 plus e power minus Z out. So that is 0.7108. So forward pass is clear. There is no problem. It is just straightforward. Now the entire training is actually happening in the backward pass, that is the back propagation. So to do that, we have to compute the loss. As I said, our target was t is equal to 1. Okay, so uh, that was the actual value for the output, and what we predicted is 0.71. So the error is half of t minus y the whole square, that is 0.0418. So the entire goal using the gradient descent is to minimize this error. So what we do is we assume the learning rate to be 0.1. So as I said, that this is a hyper parameter that needs to be tuned while you are training your neural network. Usually it is trained empirically only by selecting different values for the learning rate and then looking at its impact on the minimization. Okay. So you may plot a graph with epoch versus the learning rate, or the learning rate with the minimum loss, etc., to decide on this parameter. Now we want to train this neural network by first training this set of weights, that is V1 V2, and then secondly training these set of weights. Okay. So we will use gradient descent for that. The update rule for gradient descent is the V I plus 1 will be updated using Vi minus eta times the gradient of error with respect to Vi. So what that will be, we will use uh, the chain rule. So our error is t minus y the whole square. Okay, the t minus y the whole square. So gradient is basically the partial derivative. So delta e upon delta v1 first we will do with respect to v1. Y is dependent on z output, and z output is dependent on v1. So we will have three terms in the chain rule. So that will be the partial derivative of e with respect to y, partial derivative of y respect to z out, and partial derivative of z out with respect to v1. So these can be calculated using what we already have. So we know that e is equal to half t minus y the whole square. So when we differentiate this partially with respect to y, you will get it as t minus y. And you also have the expression for y, which is the sigma of z out, so whose partial derivatives with respect to z out also can be found out. And finally so that is equal to y times 1 minus y. So you can calculate this. The partial derivative of the sigmoid function comes out to be this. And you also have the equation for z out here. So when you take the partial derivative of z out with respect to v1, you get h1. And you have all the values here present. So this way you can find the gradient, okay? And substitute in the update rule to get the next set of weight. So this way you can find the other weight also for the next iteration, and this comes to be zero point 0.5 for v1 and 0.6 for v2. Now comes the second part wherein we want to update the second set of weights, that is these weights, okay? So these weights are updated again using the gradient descent, using the back propagation and the chain rule. In this case, we will update each of them with the help of the update rule from the gradient descent. So the update rule says that the weights W11 will be updated using the previous weight minus the learning rate times the change of error with respect to W11. Okay, so we will try to find this out. So let me give you that entire expression here. So W11 will be updated. So let me keep it as dash, will be updated as W11 minus eta times del E upon del W11. So that is equal to W11 minus eta times. So E is dependent on Y. Y is dependent on Z out. Z out is dependent on so Z out is dependent on, let me check back here, H2. Yes, so this is dependent on H2 and H1, and these are dependent on Z1, and Z1 is dependent on W11. So what we will take is upon H1 and H1 with respect to 1, 1. So this is the, I'm sorry, my pen is not writing well today. Something wrong with it. I will get it corrected for the next session. So this is the entire chain rule. So we are finding this gradient of the error with respect to W11 using this chain rule. That is, first we find the change of this error with respect to Y. Then we find the change of Y with respect to Z out. Then we find the change of Z out with respect to H1, and then we find the change of H1 with respect to W11. Similarly, you can find the value for W12 dash. Okay, W12 minus eta times delta E upon delta Y upon delta Z out times delta Z out upon delta H2 and H2 upon W12. Okay, so this way the chain rule works, and you have all the values for them. So we here in this slide we have saved the delta out, I mean this particular change in a variable called z delta out, and then we use it to further find this part, that is use the other part of the chain rule, that is with respect to H1 and then H1 with respect to Z1. So finally we only have to we have only one term left here, so that is taken care in the next term. So this is giving us the total gradient of the weights W11, 12, 21 and 22 as these. And finally, we make the update of W11, 12, 21 and 22 using the calculated gradients and the learning rate and the previous weights. So this is how the weights have been updated, the first set of weights. And then you find the, again you do the forward pass and find your Z1 dash, Z2 dash, H1 dash, H2 dash, and so on. And then you find your Z out dash, and then finally you find your final output that comes out to be 0.71, which is still not close to 1, and this is the error that you get again. So you see how the gradient descent is working and how much slow it is. In the previous step you got I mean in the first step, I think in the with the first forward pass you got the error to be 0.0418, and with this one update you have got it to be 0.0414. So that is very very less updation that has happened. So this is very slow, and it converges very slow. So that is why you have to take the data set in batches and perform gradient descent on it. This is called the stochastic gradient descent, which computes the gradient using mini batch per iteration. Okay, so this introduces a kind of randomness by selecting only small batches of updates. This way, the algorithm works faster and converges a bit faster than what it does for the simple vanilla gradient descent. So, simple gradient descent is also referred to as vanilla gradient descent in many of the neural network problems. So, update rule remains the same. Only the difference is that it is applied on a mini batch of the data point. So, advantage, as I said, it converges faster and practically better for larger data set. But there are challenges in this also. This updates all parameters at once, regardless of their varying needs. That means if there are some features which do not require the same updates as the other ones, then there is a misrepresentation. Okay, so this is a challenge that is taken care in the next optimizer. And this is sensitive to learning rate tuning. So if you if you change the value of eta learning rate from zero point 0.1 to say 0.12, that also may create a lot of variance in your output. And of course it may get stuck in the local minima or saddle point. So saddle point is nothing but a point of inflections in the higher domains, okay, where you do not have a maxima nor a minimum. So this is an example of a data set on which the stochastic gradient descent works very well. Why? Because this is a small, clean and a structured data with well-behaved gradients. That is, they do not vanish or they do not diminish or they do not go very large. So that way, this data of 178 samples, which is very structured, numeric, clean data with no outliers, the SGD, stochastic gradient descent, works very less. So this data set, these kinds of data sets are suitable for performing the stochastic gradient descent, and it works well for these kinds of data. So now the disadvantage that it comes up, the stochastic gradient descent comes up with is that it cannot work with the loss surfaces which are having complex topography. Okay, so or it may be very slow in those kind of loss functions which are a bit complex. Okay, or the data sets which do not have well behaved gradients. Okay, so the problem of slow convergence is taken care of in momentum. That is, there is something called as stochastic gradient descent with momentum. So for example, I'll give you an analogy as to why this momentum is required. So think of this SGD like pushing the ball that rolls based on the current slope. So if the slope keeps changing directions, like in a zigzag fashion, the ball jerks around. Okay, and momentum uh, momentum, what it does is it lets the ball build its own velocity so that it can push through the small bumps and it can glide smoothly towards the minimum. Okay, so this is what I meant when I said that SGD will not work very well when the topology of the loss surface is very bumpy or very ravine like. Okay, so in that case we require something called as momentum, that is giving uh, giving a smoothness towards the convergence process. So the update rule for the SGD with momentum is given by delta xt is equal to beta times delta xt minus 1 minus eta times the gradient of the loss function. Okay, so this means that the current update, that is the change for the next update, is a combination of fraction of the previous update, that is delta x t minus 1, and the current negative gradient. Okay, that is gradient of L of x of t. So instead of only considering the current slope like the vanilla gradient, this adds inertia from the past movement. Okay, that is what is called momentum. Okay, so in this plot you can see this is again a contour plot of a 2D function. It shows a loss surface. Okay, and this path, as you see, that initially it has quite a zigzag manner. Okay, so this is the trajectory with which the optimizer is approaching the minimum point, that is this point, that is the final convergence point. And here you can see that the update direction, that is delta xt, and the previous update direction delta xt minus 1 are aligned. Okay, because momentum is building up in this direction. Okay, so from here the momentum is building up and it is helping to slow down these kinds of zigzag movements, and hence as a result the entire convergence process has been speeded up. Okay, so SGD with momentum is fixing this instability and inefficiency of the vanilla SGD, that is the usual SGD that we saw without the momentum, by incorporating this momentum term, which is taking into account the past gradient information, and hence it is helping stabilize the update direction, accelerating the convergence. But there is again a challenge in this also. Sometimes the momentum, so when the contour, I mean when the topology of the loss surface is not this ravine in nature, or it is not bumpy in nature, in that case what momentum can do is it can overshoot the minimum. So that we will come to a bit later. I mean, as I already told you, the advantages and disadvantages are that it can overshoot. So what happens is SGD with momentum is also applying the same learning rate to all parameters. So that means that was the case with vanilla gradient also. It was applying the same learning rate to all the parameters. However, there are certain data sets in which some features are very frequent and some are not that frequent. For example, the data sets in natural language processing, they consist of rare features which require constant updates. But SGD and SGD with momentum, what they are doing is the main features get updated a lot because of their gradients appear quite often, whereas in the rare features they get updated less frequently but with the same learning rate. So as a result, the rare features learn very slowly or sometimes almost not at all, because the learning rate is not adapted according to their frequency. So momentum also keeps accumulating these past gradients. So if a feature has a consistently high gradient, it keeps pushing updates, potentially overshooting. And that's when the adaptive gradient optimizer comes into picture, that is the ADA-GRAD. So what it does is it adapts the learning rate individually for each parameter based on the sum of squares of the past gradients. Okay, so parameters with large frequent gradients get their learning rate reduced over time, and parameters with small or rare gradients keep a relatively high learning rate. So this is because of this new learning rate, that is eta upon square root of gt plus epsilon times this gt. So what are these? Let us see. So here the theta t is the parameter at the time step t. Eta is the initial learning rate, as we have already seen in the case of SGDs. GT, the small gt, is the gradient at time step t. This dot is the element wise multiplication, and this entire term is the adjusted learning rate for each parameter based on the past gradients. Okay, where this capital GT is the sum of squares of the past gradients. It accumulates over time, increasing for parameters with large or frequent gradients, and um, uh, and at the same time for rare parameters it adjusts the the learning rate. Okay, it keeps it relatively higher. Okay, so as you can see, if this value is low, this entire thing becomes high. If this is low, if this is high, this entire learning rate is becoming lower. So this is how the learning rate is getting adapted as per the frequency of the features. And this solves the problem of overshooting as well as the misrepresentation or the not so learning with the frequent and the not so frequent parameters. So this makes AdaGrad especially useful for sparse data like that of natural language processing or the recommendation system, where some features occur less frequently than the others. So this is an example of such a data. This is a data from sentiment analysis, is some kind of text having the sentiment of it. Okay, so AdaGrad works very well for these. Now AdaGrad also has certain disadvantages, that is it is using only the I mean, only accumulating gradients. Okay, so if the data set is not sparse, then the gradients they become they accumulate over time, and they become so large that what happens, this entire learning rate stops. It becomes very small, and the entire learning process comes to a stall. Okay, so that is when we require this another optimizer, that is the RMS prop. Okay, which makes use of moving average, exponential moving average. So this is again another adaptive learning rate optimizer, which is designed to overcome the diminishing learning rate problem in the AdaGrad. So in AdaGrad, we had only this GT square, capital GT square. In RMS prop, this is now given by this formula. That is the squared gradients are taken by the exponentially moving averages of the gradient. Okay, so this is the key part of how RMS prop works to adjust the learning rate for each parameter individually. So why using a moving average? The goal is that to prevent the oscillations in the steep directions. So supposing you have a loss surface which is very steep only in the y direction, but it is not that steep in the x direction. In that case, what happens is that if you are using AdaGrad, what happens is because of gradients accumulating, the squared gradients accumulating, it is giving a higher learning rate only to the y, only to the y axis. Okay, whereas the x1 is not updated that high. So it is the entire process will result in higher initial jumps and low convergence. So to prevent these kind of things, you have the exponentially moving average. So if your recent gradients are large, then uh, what happens, this entire step size becomes smaller. If your recent gradients is small, this entire step size becomes larger. So this is especially helpful when one of the direction is steeper and another is not. So RMS prop avoids this vanishing learning rate, which was happening in the ADA and it keeps the optimization going. So again, this now you have the two parameters here. One is the learning rate and another one is this beta, that is the decay rate. So usually it is taken to be 0.9, or again this is a hyperparameter which needs to be tuned as per the as per your neural network. So to demonstrate this this fact, I mean, what you say, the RMS prop and ADA, you can try out this problem of optimizing, say, f of theta is equal to half of theta square. Okay, so you can try to implement both RMS prop and ADA on this and see the result by taking your initial theta naught as 10, and say learning rate I can give you as 1, decay rate, so decay rate, so let me take the decay rate beta to be 0.9, and the initial g naught to be 0. And for now you can avoid taking the, I mean, you can take epsilon to be very, very small, or you can also uh, I mean, manual calculation, you can take this in both the optimizers, and you can see that the update with RMS prop is more consistent and it is converging faster to the minima as compared to that of ADA grid. Okay, so at one point the ADA grid will stop the learning process because the gradients are accumulating and it becomes very large, and hence the entire step size becomes very, very small. Okay, so this data set is a perfect example for using RMS prop. So this data set combines the time series sensor data, which is in the form of image, and the data is very sparse, noisy, and has uneven gradients. So in these cases, RMS prop is the best to use because it handles the noisy gradient well because of the moving exponentially moving average, and it adapts the learning rates on a per weight basis, helping in training with uneven or sparse features. Now, RMS prop also comes up with challenges because it is, as you can see in the update rule, it is only using the magnitude of the gradient. Okay. Um, so we will see how this is handled. So first of all, you can see here there is this 3D plot, okay, of this function 0.1 x square plus y square. So you see that this function is really steep on the y axis and not very steep on the x axis. So in this case, the RMS prop will not work very well. Okay, so you can see here now, we will demonstrate it using the numerical. So we are taking the decay rate to be 0.9, and we are taking epsilon to be 0 only for mathematical ease, and initial point we start with 1 1, and the initial squared gradient accumulator we are starting with 0 0. So the step one is to calculate the G1, the squared gradient, and then we find the exponentially moving average using this formula that we saw here. So this is the formula that we are making use of. We are representing this by nu 1. Okay. So we took the decay constant as 0.9, and we have assumed nu naught to be 0 plus 1 minus 0.9 times the square of the gradient. So that gives us, because this is a element wise multiplication, so we are getting this to be 0.004 comma 0.4. So next step is to update use the update rule. So that is theta naught minus the learning rate times g1 divided by root of v1 plus epsilon. So this is going to be theta naught, we have assumed to be 1 1. That is where we are starting. We are starting this to find the next point. Eta we have assumed to be 0.1, that is the assumed learning rate here, which is a hyperparameter. And g1, we have got it to be 0.2 and 2. Why? Because our function is 0.1 x square plus y square. So when you take the gradient of it, it will be 0.2x comma 2y. And because we are starting with x naught y naught 1 1, so the first set of g1 is going to be 0.2 comma 2. So this is how you have updated the weight. So we are taking epsilon to be 0 for the time being, for the ease of calculations. So this is after simplification and performing the element wise multiplication, you get the next updated um, value to be 0.68 comma 0.68. Similarly, you update the second time with with the previous value. Find the gradient. Put the gradient value of x and y as 0.68 and 0.68 in the gradient. Square it. Find the exponentially moving average, and then find the update. You will get the next point to be 0.47 or 0.5 comma 0.5 if I'm approximating it correctly. And this way you perform the procedure iteratively. You will see that what is happening. Initially there is a big jump here, okay, and you are having, initially there is a big jump and afterwards it is slowing down, okay. So this is because of the uh, steepness on the y-axis part, okay. This is a disadvantage of RMS prop. It makes a large initial jump, but then begins to slow down due to the large value of the exponential moving average, especially in the y direction. Okay. So the this disadvantage of RMS prop is because it is only taking the magnitude of the gradient and not the direction. So it does not track the gradient direction. It only makes use of the magnitude. So what happens in a very ravine shaped loss surfaces, the gradient, where the gradient changes abruptly, bouncing side by side, RMS prop ends up making zigzag turns. So that's where the adaptive moment estimation, that is the ADAM, comes into picture, which combines the advantages of these two extensions of momentum as well as RMS prop. So momentum, why momentum? Because what RMS prop was lacking, it was lacking direction. So momentum is providing that direction. So the update rules for Adam are like this. So here you can see the MT. MT is the momentum like behavior that smoothens the gradient. VT is RMS prop like behavior that adapts based on the gradient magnitude, and it helps in the adaptive learning rate. And then you have the bias correction for both these M hat, the momentum as well as the VT, that is the RMS prop type. Okay. So why these are important? Because in initially M naught and V naught is equal to 0. So early values of MT and VT are biased towards 0. So this bias gets smaller as your T increases, as you increase with the time. As you increase with the number of iteration, the bias gets smaller, but is problematic at the beginning of the training. So statistically also you can see that this bias is required, this bias correctness is required. Why? Because if you see that if you take the gradient to be the random variable, uh, you consider the gradient to be a random variable and assume that all these gradients gradient random variables have the same expected value. Okay. So in order to estimate the expected value of this gradient, we apply the expected value formula, and then we see that the mt, that is the expected value of mt is basically correction factor times that value mu. So there, this 1 minus beta 1 or 1 minus beta 2 appears as a correction factor which needs to be taken as a bias correctness. If this is not taken, then the results will be misleading because there will be bias towards 0. So bias in MT arises because it starts from 0 and it uses the exponential averaging. So the expected value is calculated. So if you want to see the derivation, you can calculate the expected value, assuming the gradient to be a random variable, and assuming that the expected value of all the gradients at all the time is mu, that is the mean value. Okay, and then you calculate using the statistical formula. You will arrive at the fact that E of MT, that is expected value of this MT, is going to give you mu times 1 minus beta 1. Okay, so that is why this correction factor has been added in both the terms. So here you similarly you have the correction factor in VT also. So here you have the update rule, final update rule, which is combining this VT, VT cap and MT cap, where your MT is the momentum and VT is your exponentially moving average. Okay, and again epsilon is added because we do not want the division by 0, so it is providing kind of numerical stability. So atom basically works on kind of all the complex data. It is for general purpose, and natural so here is an example of a data set on which adam works. So basically adam is used for image processing data sets where convolution neural networks are trained, and you have very very dense gradients. So in those cases you don't already you have you will want to have a high computation power because you are processing uh, data set which is image data set, so that itself is very computationally heavy. So you don't want the training process also to be going very slow and computationally heavy. So that's where the adam is performing very efficiently on complex and high dimensional input as well. So here is the same example that we saw for the RMS prop, in which we saw that RMS prop was getting slower after having initial good initial jumps. So the same example, if we try to solve it using the atom, what we see is, so we take the momentum beta 1 to be zero point 0.9 and RMS decay, that is the second moment. So these are called first moment and second moment also to be 0.999. So these are also hyperparameters. However, the authors who first introduced Adam, they empirically showed that it works best for beta 1 is equal to 0.9 and beta 2 is equal to 0.99. So mostly people use that, or they can just they can use the tuning to tune these hyperparameters as per their needs. We start again with the 0.11, and we start with m naught and v naught to be 0 0. And we see that when in the step 1 the gradient is 0.22, m1 is a zero point 0.9 times, that is beta 1 times the m0 plus 1 minus beta 1 times the gradient, and v1 is beta 2 times the v naught plus 1 minus beta 2 times the gradient square. Okay, so these we substitute in the bias correction terms, and then we find the update using the final update rule with the bias corrected terms, and we get our next update as 0.9 and zero point 0.9. Similarly, for the second step, we do the same thing and we get the next update to be 0.8 and 0.8. So now you see here, unlike the RMS prop, there are no initial jumps. and it is converging very quickly to the minimum point. Okay, so this is how the atom works very nicely. So here is the comparison of RMS prop and atom on the same example, and you can see that the atom is following the optimization process, or the process of getting to the minimum very consistently without having these oscillations, unlike this RMS prop on this particular function, which is very steep with respect to y and not that steep with respect to x. So this plot has been done in the Python with the Adam and RMS prop. So you can, I don't know if you can make out, but RMS prop is quite slower, and it is zigzagging. Okay, whereas Adam is very smooth. So as I told you, RMS prop makes large initial jumps but then begins slowing down due to large VT, especially in the y direction. Adam keeps moving more consistently and smoothly because of the momentum term. And this is finally the comparison of all the optimizers that we have seen: SGD with momentum, Adagrad, uh, uh, prop and Adam on the function x cube minus 3xy plus y cube. So this is the contour plot of this function, and this point is the minimum point. And this is how the various optimizers they are performing on this function to reach to the minimum point, and all of them have the different trajectory. So if we look at the zoomed picture of these optimizers, you see that the momentum SGD with momentum is kind of overshooting. So this blue line is for SGD with momentum, so it is kind of overshooting the minimum, and then coming back and converging to the minimum. So this also is a little worrisome. Adagrad is a bit smoother, and RMS prop is also a bit smoother. On this particular function, Adam is also a kind of overshooting. So this depends, as I told you, the various scenarios for which the optimizers will perform better. So for SGD, it is best for large, well-curated data set, well-behaved gradients with consistent patterns. So, and it is commonly seen in image classifications or CNNs, where you can divide in different batches, and you have very nice features in numeric form and so on. Adagrad is suited for sparse data with infrequent features like that of natural language processing or click data. These are commonly used in text or text classification, or the recommendation system, sentiment analysis. RMS prop is best for noisy or sequential data where patterns evolve over time. So, and your data set is time dependent, it is not stationary. So this is most commonly used in time series or speech analysis or the recurrent neural networks. Adam is for general purpose, it has fast convergence, large scale data sets, deep networks, noisy gradients, it can handle it all because it is using the advantages from RMS prop and SGD with momentum. So it is commonly used in the very complex models such as BERT or GPT in natural language processing, image segmentation models. So this is about the brief comparison of optimizers. And with this, I end this talk and will be happy to take any